Work, power, and machines. So what is work? Huh? Well, I can put, you say force? Yeah, force times the distance. Well, you're taking pressure times area, but this. So all these people right here doing work, right? The product of the force applied to the object and the distance to which the object to which that force is applied, right? So what they're saying is we got to do work, we got to have what? Force and distance, right? Everybody okay? That makes sense. So if you mow the lawn, are you doing work? All right. If you're lifting weights, are you doing work? Okay. If you're moving furniture, are you doing work? If you're pushing against a locked door, are you doing work? No, why? No, don't get distance, right? Swinging a golf club, does that work? Yep. Sorry, guys. Calculating work. So this is the formula, big hard formula. It's basically like our work, right? When we calculate power, but instead of using distance, we're using speed. So our force is voltage, right? And our speed is current. So what's 1 amp equal to? Anybody know? 6.28 times 10 to the 13th electrons moving past a point in the circuit at any one time. That's and I counted them, right? All the part of the work must be acting in the direction of the motion, right? Do you do more work when you finish the work quickly? Right? No work is done when you stand in place and hold an object, right? By the way, these are not my PowerPoint. Well, I already looked at this, right? Work time distance, you're okay. Right? Of course, it depends on what you did. Over here, what's our measurement for force over here? Or work. How do we measure work? We usually measure it in something called foot-pounds. Right? Our torque, we do it in diameter, how far it moves, but it's basically that. So we'll look at this. U.S. customary is in what? Feet pounds, foot pounds. That's not feet pounds, that's foot pounds. Pounds times feet is what it's saying. So there we go. But we don't say feet pounds, we say foot pounds over. And we don't need to know this, even though we need to know who some of it's named about. So power is how quickly work is done, the amount of work done per unit of time. So if two people mow 2 lawns of equal size and one does the job in half the time, who does the most work? Same work. So what happens is it's force times distance, right? You understand that? So if you travel the distance faster, you're doing the same work. So this is what we're saying. If you jog No, I think, yeah. Power equals work times time, or divided by time, right? We okay? So if work goes down, time goes up. The watt, y'all familiar with the watt? I knew it's named after. What's watt? What's watt? We use that all the time. Yeah, that's power, right? Of course, we use it as electrical power. And then we got three formulas that we calculated. What's the three formulas that we use to calculate power? Ohms times voltage. What's the other two?
Squared divided by
Something squared. So, everybody got this one. Power is equal to V or E. You know, E is used a lot too. So E is electromotive force. So you'll see that used a lot instead of using V. And basically it actually is better because what we're doing is we're folks solving for folks. Does that make sense? So the power is equal to V times I. Now what does Ohm's law say I is equal to? No, I is equal to what? V over R. Right. Wait a minute. Yeah, this is what we're doing. So what it says is I can come up here. If this is true, then what can I do? Well, I can substitute this for that right there. So now we're saying P is equal to V over 1 times V over R. So power would be also equal to V squared over R. So that's our other point. But where did it come from? Well, it came from substituting what? Ohm's law into Watt's law. So so if I is equal to this, what's V equal to? It's equal to I times R. So I can substitute that in there. So now we're saying power is equal to V times, right? I'm sorry, I'm substituting for V. Let me get y'all confused. So what's V? It's equal to I times R, right? Everybody understand that? Times I. So our other formula is P is equal to I squared R. So that's our three formulas for calculating power. But they all came from where? They all came from this guy right here. Huh? I did. Yeah, I know y'all's name now. I don't have to call Rowe. I just see who's here and who's not here. Here, when I do Rowe, I'll come back and put a card in there. We're supposed to say, hey, Rick, I'm here, right? Oh, I didn't want to keep that. So this tells us about invented. So James Watt invented that. This is history. It's not me to know. Okay, I need to take those slides out. Horsepower. Yeah, 776. We use 776, but it's actually 745.5 something. Well, we just go ahead and round it because it's close enough to do. It's close enough for government work, right? Because what we have to understand is that in electronics, nothing. It's like when I do math and I use yeah. So when I'm doing math, so back in DC, what did you have to do to all your resistors? You had to measure because you were trying to prove Ohm's law. So when you did your calculations, you didn't use your color coded value. You're supposed to use your measured value, so you could see that V is equal to I times R. But once you get into your advanced classes, we understand that everything has a tolerance. So when we say we have a 100 ohm resistor and we calculate it, and we calculate current to be 450 milliamps, and it comes to be 457, we say that's okay, right? So what it is, it's easier for people to remember whole numbers than it is for them to remember what? Fractions. Does that make sense? And it's going to be close enough, right? So once you include the efficiency of the system, it's still going to be close enough to tell if you're what, if you're right or wrong. And if you take solid state, guys, we do a lot of approximations in solid state. So I might calculate 10 volts and I might measure 8, and we say, okay, that's okay, because of not only do we have the tolerances for the resistors, we got the tolerances for the solid state devices themselves. So everything has a tolerance. So we would say horsepower is equal to 746 watts per horsepower times the efficiency of the system, right? So what you're going to find out, usually you're going to put more than 446 watts into it to get 446 watts out. So this is what they basically did. What they did, of course, is that at the time that these guys came out, when they were trying to compare the work of a steam engine to the work of a horse, because everybody knew what? Everybody knew horses. They'd been plowing fields, and they knew how the horses, they knew how much they could pull. So what they did is they took some horses and took a bunch of them. They hooked them up to a weight. I think it was like 550 pounds. And then they dropped it down in the well, and they saw how far the horse could pull that weight in a certain amount of time. And they did a lot of horses, and they came up and got an average. And then they compared that to what the steam engine could do. And that's where the horsepower came up with. That's how they came up with it. The team of horses would develop a quality of power of stone horse, so they used a lot of them, right? 550 pounds or 750 objects in 1 meter in 1 second. So it was an average. I can't remember how far they actually pulled. And that's what they came up with, the average. And then they converted that over to 550 pounds. And I don't know why the guy put the arrow pointing into the horses. I did lower this, guys, by the way. It was, what is a machine?
Nice.
Well, probably that basically makes work easier, right, for us. So we use it to make work easier. A device that makes, I hit that note, make work easier. A machine can change the size, the direction, and the distance over which a force is applied or acts. Are we okay? So we have two types of forces. So we have a force in and we have a force out. And anytime we calculate a mechanical advantage, how do we calculate mechanical advantage? Anytime we calculate a gain, it's a standard formula. So anybody know how you calculate a gain? So it's out divided by in. Just that simple. No matter what gain it is. So if I've got an amplifier in my car and I want to calculate the power gain, I would measure the power out and the power in. And it will come up and give me. So what we have is we have a force in and we have a force out. Force is what does work. Right? So we can't get work without force, and we can't get work without that force causing something to move. So we have input force. This is a force applied by the machine or to the machine. So this is what we put into it. So like our combustion engines, we're putting what into to get force? We're putting gasoline, right? And then of course we're getting torque out. And then we have the output force. This is the force that's being applied by the machine. Are we okay? Or we could say the force in would be the force that we're applying to the machine. I'm applying to the machine, right? Two forces, so we have work in, so what we have to do is we have work input, we have the work done on a machine, right? And then of course the work. So what is it? So here we go. So work is equal to what? Times the what? The distance to which the force is applied. So that's what we're going to do. You can see what's going to happen. So we can either do one, two things with the output, with the machine. We can do what? We can increase the distance. If we increase the distance, the speed goes up, the force has got to go down, right? You understand that? If we increase the force, then if we increase the force, then the speed's going to go down. Because work in is supposed to equal the work out times what? The efficiency of the system.
Increase the force, you decrease the distance.
No, on our output, not on the input, right? So what we're going to do on our input is we're going to apply a force to cause it to go over us that causes our engine to turn a certain distance. And then we're going to run that through some type of gearbox, which is going to determine the distance that the wheels move, right? You understand? But it still works. So if a machine was 100% efficient, then work in would equal to work out. That would be called an ideal machine, is what we call it.
Something motion.
Well, they call it perpetual motion. So if that was true, then I could take the output of a machine and feed it back into the input of the machine, and the machine will run forever. So there was a video on YouTube that popped up on one of my things about a guy that had a little DC motor, had two big old magnets, and he rolled a coil of wire, and he would put them down. He'd put the coil of wire into the coil, and the motor would spin. And he wasn't moving the wire or anything, right? So he had no motion on the wire. But yet the motor was set up for spin. And he'd pick it up, and the motor would go off, and he'd put it down, and the motor would come on. And there's quite a few physicists that said this was impossible. And they said, what he was probably doing was he had a blow dryer over here somewhere. And every time he'd put it in there, he'd do what? And there was another one we saw where a guy had a motor, and he had the motor turned into a generator. And then what he did, he fed the generator back in the motor, and then he unplugged the motor, and everything kept running. So that would be perpetual energy. That's impossible. Never. So we never, ever get more work out than we put in, right? So work output, so we figure our work input. So our work input is going to be what force we put into it, and how far does it cause that to move. And then our output is going to be the work done by the machine. So this is going to be the output force times the distance that the output does. So what we're saying, if work in equals work out, if my output has more force, it's got to be running at a different speed, right? You understand? That's gears.
You got something like gravity, friction.
Yeah, that friction. Friction is a big thing, and overcoming gravity. So if you're lifting something, then that would be the form of friction. You're working against what? You're working against gravity. So there's no such thing as a machine is 100% efficient. So that would say you have absolutely no friction, no gravity or anything. Right? Can you get more work out than you put in? No. Can't get more work out. In fact, the work we get out will always be a little less than the work we put in. Work output can never be greater than the work we put in. Can never be greater. Basic law of physics, right? If you ever see anybody that does that, you know it's something going on, right? So mechanical advantage, we've already talked about this. How do we calculate mechanical advantage? Yeah, what you get out over what you get in, right? The number of times the machine multiplies the input force, so mechanical advantage is equal to the output force divided by the input force. So this is what we can use. Or we could use the output distance divided by the input distance. So it's kind of like a gear. So you got several ways you can calculate the torque you get out of a gear, right? Types of mechanical advantage. We have ideal, which is what we deal with a lot. It involves no friction, right? And then we have what we call the actual, which would be what? It involves friction, calculation. So it would be calculating the ideal, and you would multiply that times the what? Efficiency, but the efficiency is always going to be what? That's one. This makes sense. Everybody okay? So if the output is equal to the input, right? Of course, this will never be true. It's always going to be a little less. So this would be a mechanical advantage of 1. We could change the direction, but not the force. So we use these a lot. So if I've got 2 gears, that's exactly the exact same teeth number, right? You understand? And what we'd be doing with that would be basically to mesh them together. And your driven is going to be turning in the opposite direction of your driver, but they're going to be at the same speed, right? So if you got an ideal mechanical advantage of 1, then that means your distance is going to be the same. So these guys are seesawing. Now, how could we get a mechanical advantage of 1 on a seesaw? First of all, we'd have to have the same weight people on both sides, right? You understand? And the fulcrum would have to be exactly in the middle. And what usually happens there? Y'all ever tried to do that try to balance? Usually what you do is you move closer. Mechanical advantage of less than 1. What you do is you get an increase in distance. What? Y'all understand that? Yes or no? So if mechanical advantage is less than 1, then we're going to get an increase of distance, right? But a decrease in what? Force on the output, right? So a rake. So efficiency can never be greater than 1. Why is that? Friction. Where you're saying it takes nothing to run the machine. So even in power amplifiers, so if you got a 100-watt power amplifier in your car, you're going to have to put more than 100 watts into it. Your battery's going to have to provide more than 100 watts into it because of the efficiency of the watt of the amplifier itself. Some work is always needed to overcome friction. A percentage comparison of workout, what we're working in, right? We okay? We're already. The lever. So this is the getting into the lever. So tell me the different types of lever we have. Anybody know?
Crowbar.
Well, that's a lever, but what types of levers do we have? Okay. So we have 3 types of levers. They're called a type 1, type 2, type 3 lever. So type 1 lever is a bar that's free to pivot or move. So this is a lever. This is not type 1. So this is a lever, a bar that is free to pivot or move about a fixed point with an input force is applied. The fulcrum is the pivot point of the lever, right? Everybody okay there? There are 3 classes. This is what I was talking about. There are 3 classes of levers based on the position of the force and, of course, where the fulcrum's at. And I used one of these just the other day. Are we okay? Yes? No? So first class lever. So what's a first class lever? Y'all seen this. So a seesaw is a first class lever. So the fulcrum is between your input force and your output force. It's not necessarily in the center, but it's somewhere between them. Where the fulcrum is positioned at depends on what type of mechanical advantage you get. So if the fulcrum was exactly in the center, then you would get a mechanical advantage of 1. So if you put 100 pounds in, you'll get 100 pounds out. The closer you move it to your output, the better your mechanical advantage gets. But what happens is the closer you get it to your output, distance goes down. Fulcrum is located between the effort and the resistance. Makes work easier by multiplying the effort force and changes direction. So seesaws change direction. So when you push down on one side, the other person does what? Goes up. So here's an example, of course. pliers. These are pliers. These are class 1. These are class 1 levers. Here's your fulcrum right there. See that? Here's your resistance. Here's your effort out here. And notice the distance here. So this is a lot shorter than this right here. So this means this guy's going to be a force multiplier, right? Understand? But over here, I'm going to have to travel a further distance. Over here, it's going to be a shorter distance. So if your force goes up, your distance on your force on your output, if your force goes up, your distance has got to do what? You can see this everybody's used pliers. So you're over here open them way up, and your jaws over here are only open a little bit, right? You understand? Because what are you getting out of that? You're getting a force multiplier. So here's a pair of scissors. That's basically the same thing. Crowbar. This is what Tucker's been saying. Now look where the fulcrum's at right here. So the longer this handle is, guys, the more distance you're going to have to travel when you push down, right? You understand? Which means the other one is going to go at a shorter distance, but you're going to get a lot of what? Force multiplication. If it's exactly in the center, then your mechanical advantage would be 1. So that means if you put 100 pounds of force over here, you would get 100 pounds of force over there. But depending on where you put the fulcrum, the closer it gets to you, or the closer it gets to you where you're applying the force, the mechanical advantage is below 1. If it's in the center, it would be 1. And the closer you get to the resistance or the load, the mechanical advantage goes up. Right? You understand? So mechanical advantage is dealing with you're either going to multiply force or you're going to multiply speed, right? So it's just like a gear. Now, most of the time when we use levers, and that's not true. So a baseball bat, what are you getting out of a baseball bat? So I'm over here, right? You understand? And I swing it. My baseball bat is traveling. So I'm traveling a distance right here. My baseball bat is traveling a distance out there. So a baseball bat is a speed multiplier. So it means it's going to be a force divider, right? Second class lever. So if a first class lever, if the fulcrum is between the resistance and the input and the output, then where's the second class lever? I just used this from the other day. Huh? So the fulcrum is going to be on the end, and then your output force is going to be I can't say in the center, between the fulcrum and you. So I used this the other day, my tractor. I was riding along, I got a 0 turn because I couldn't do a clutch anyway. And I was zipping along, and all of a sudden the sucker just went dead. And what had happened is that when I was cutting some of my neighbor's grass, the side of my tractor got into a bush. It pulled out one of my wiring harnesses, pulled off a connector, and two of the hot wires. No, they touched together and blew the fuse. So I was zipping along, and those 2 wires touched together, and it just went dead. So I disconnected the wheels, and I could not push that long. I could not push it. Of course, I have a bum leg anyway. So what did I do? Well, I just got me a big 2x4, right? And it's about this far, and I had an 8-foot 2x4, right? You understand? And I moved that tractor with no problem at all. But I was only doing it. I was going 5 feet, and the tractor was going 6 inches. But I was able to move it and get it back to my house. So this one, the lever is on the end. So what I was doing is I was planting my 2x4 into the ground, right? You understand? And then I was pushing my lawnmower with that. I used it again too on my lawnmower too when I was trying to drop the wheels out so I could grease them.
These guys take cars off the flatbed, damn do like that. Slide them down.
So a wheelbarrow is a class 2 lever, right? And a door is a class 2 lever. And just think about how far you open the door and how far the hinges move. Very, very short, right? So the next lever we have is a class 3 lever, third class lever. Effort force is located between the resistance and the fulcrum. Does not multiply the effort, only multiplies the distance. So baseball bat. So you're out, your fulcrum is all the way on the very end, right? So what you're doing is you're getting a speed multiplier, right, or a distance multiplier, but you're a lot of force. A tennis racket. So you're back here on the back of the tennis racket, right? So the end of the tennis racket is moving quite a bit of distance compared to your arm. A shovel. A shovel does this too, right? Are we okay? Of course, that guy's shoveling snow. Now, yeah, weight. So you're a weight. So here's your fulcrum back here at your elbow. So here's the levers. So class 1 lever, class 2 lever, class 3 lever, class 3 lever. You can see these guys right here. These are going to have, you're basically lifting up the weight, right? You understand? So I've used this one before. I've used, probably every one of y'all's used it. What type of lever is this? What type of lever?
Class 1.
This is the first question. The fulcrum. So here's my word. Here's my force. Here's my output force. So your fulcrum on a class 1 lever, the fulcrum is between you and what you're trying to move. Right? A class 2 lever, a class 2 lever, the fulcrum's on the end, and the work's in between you and the force, right? And then on class 3 lever, right? So on a class 3 lever, look at the difference of where the work is. So the work is up here with you, right? You understand, right here. So if this right here was 300 pounds, guys, I would be picking up 300 pounds. A wheel. Fixing them. So it's almost 8 o'clock, guys. Let's go ahead and take a break, and this is a good spot